So in this video we're going to look at a range of asymptotes, how to understanding asymptotes, and it'll take probably close to 10 minutes just to get through both the explanations and a slightly more complex example. Okay, so our asymptotes are vertical asymptotes, horizontal and oblique asymptotes. The first one we look at is the vertical asymptotes, and essentially this is where x cannot exist. Okay, now, so we can't have a denominator, is the most regular case, that x cannot equal 0 in this case, and so there's an asymptote along the y-axis, and once we factorize this equation and we get this, then we know that there's asymptotes at both -2 and +3, because again, that part of the denominator is invalid when it's -2 or 3. So there's our vertical asymptotes. And that's really all you need to know for vertical asymptotes. Horizontal asymptotes, we need to consider the limit as x approaches infinity. Now, what happens is we always divide by the highest power of x. So we've got 1 divided by x and x divided by x. Now, in this case, and you know what this graph looks like, okay? So hyperbola, so we know that there's an x and y axis asymptotes. So we're dividing by x from the 1 and the x, and we get 0 over 1, so there's an asymptote at 0. In this case here, x squared is the highest power, highest degree is the way we describe it in polynomials. So we divide everything by x squared, and I get those statements there. Now, what we know is that as x approaches 0, the limit of 1 over x, so let me just write this for you. The limit of 1 over x as x approaches 0 is equal to 0. Okay, and that's why this is, when I simplify this is 1 over x, so that simplifies to 0. 1 over x squared simplifies to 0, and our numerator is 0, and that simplifies to 1, so it's 0 over 1, 0 is 0, so the limit here again is 0. Now, we'll look at an example later where that's not the case, but also it's possible to have a line, say x equals y equals 2 up along here somewhere. But that's how we find our horizontal asymptotes, taking the limit of as x approaches infinity. Okay, now our next one is understanding asymptotes is the oblique. Okay, and there's two types of oblique. And in this course, the Extension 1 course, we'll most likely see, if anything, a linear equation, a straight line that is not horizontal to the x or y axis, or not parallel to the x or y axis. For example, x plus 1 might end up being an asymptote. In this case, x plus 2 is. And how that all works out, well, there's a particular method we need to employ. We're not going to divide by x because we have a higher power on the numerator than on the denominator. So that's not going to work. We're going to manipulate this algebraically so that we have this equation being written as the sum of a rational number and, I suppose they're both rational numbers. So something without a denominator, something with a denominator. I was going to say whole number, but x, of course, can be anything. So what we've done is we've said, okay, well, let's split this thing up. And I'm just saying, look, x squared minus 4 is a convenient format because when I factorize that, which is a perfect difference of two squares, these two things will cancel. But if I'm going to add a minus 4 to the numerator, I better add a positive 4 to the numerator as well. So after we go through this process of cancelling these two things, I'm left with x plus 2, and I'm left with this fraction. So I've split the fraction. Now when I take the limit as x approaches infinity, this thing, because it's 4 over x, that thing becomes 0. And we're left with the line x plus 2, and that's the asymptote. So we would have an asymptote at x plus 2. We would also have an asymptote, notice, at 2, because that's our our asymptote there as well. The denominator cannot equal 0. Now, we're going to have a look at just a summary then of these things. And here's what we're looking at. You'll get a vertical asymptote if the degree n and d stand for numerator and denominator. So if we have a degree in the numerator which is less than a degree in the denominator. Now, what might that look like? Well, it could be simply 1 on x. Okay, it could be 1 on x plus 2. So we have x equal to -2, or just sliding it under here, we could have x over x squared. I can't really see that. X squared plus, yeah, it's getting a bit small there, but if I just take that out and start again, x over x squared minus 4, well, okay, so the denominator cannot equal +2 or -2, and that gives you a vertical. Horizontal, where the degree of the numerator is equal to the degree of the denominator. Now, we're not just talking about x over x in this case, but we might talk about x plus 2 over x plus 3. Okay, and we could divide everything by x, and we get, well, let me just change that and make that a 2x. Now, when I divide everything by x, because I'm taking the limit as x approaches infinity, x over x would give me a 1. That would be 0, that would be 0, and 2x over x gives me a 2. The limit then would give me an asymptote of y equals a half. Okay, and you can go through and have a look at that again later if you need to. An oblique, now down here we're looking at oblique, which I just showed you, where the degree of the numerator is greater than the degree of the denominator by 1. So I might have x squared over x, I might have x cubed over x squared. When we have this situation, which I won't demonstrate, we have a degree where we might have an x to the power 4, let's say 5, x to the power 5 over x to the power of 1 or 2 or 3, but more than 1. You won't see this one in extension 1, so I'm going to move straight on and do an example. Now here's the example, and I'd like you to stop now and try this before you go on. So we're going to do some algebraic manipulation to show that this is the same as this. Then we're going to try and sketch it. So press stop please and give it a go. Now here are the solutions for both parts. What we've done here, and the particular method I'm going to describe, is in this case we've been given what we're aiming for, x minus 3, and then so we split the fraction. Now, of course, what I know, first of all, I've identified a mistake. That should be a -1. So let's just fix that as we go. But you get the idea that. Let me just get rid of this. Don't want mistakes in here. Right. So what I've done is I've said, okay, so x squared over -1, x squared, that would have to cancel to leave me with x minus 3. And I would have to have a factor of x minus 3 in the numerator as well. So let's see what happens if I expand this product. And I get x cubed minus 3x squared minus x plus 3. What happens is that this minus x plus 3, there's too much. If I expand this, I have too much. I have a minus x and a plus 3. So what we do is we add an x and a minus 3 to balance or negate that those extra terms in the expansion of this product. How would you know, if this was not a show that, how would you know that this is the case? Well, here's the target, x cubed minus 3x squared. If I've got to split this fraction, I'm going to start with this sort of thing anyway. X squared minus 1, x squared minus 1. I'm going to cancel those things to get this set of brackets here. How do I know it's x minus 3? Well, basically x times x squared is going to give me an x cubed, and x squared times something has to give me 3, or negative 3x squared. So there has to be a minus 3 in here. And that's the hint. There's the link between the two things. So x minus 3 is left when I cancel these two things, and there's my final expression. And so there's my show that. Moving straight along. Okay, so we're going to sketch this thing. We consider the intersections. I'm going to fly through this a bit quickly. We're going to test for when x equals 0 and y equals 0. We find the vertical asymptotes from the denominator. So we have vertical asymptotes of positive 1 and negative 1. Now, using a, we're going to consider the limit of x approaching infinity of the fraction. Okay, and because there's an x squared on the denominator, we divide everything by x squared. And all of those terms cancel to, well, 0, 0, that's a 1, x squared over x squared, but it's got a 0 numerator. Okay, so we have a limit as if we approach infinity of 0, but that leaves me with, we go back to right at the top, this bit here, okay, x minus 3, and the asymptote then is at y equals x minus 3. What we need to do is then test what's happening as x approaches 1 from a positive side. So that means we're going from 0 to negative 0.5 to negative 0.9. So we're getting closer to negative 1 from the positive side of the asymptote. And we're testing 1, the other asymptote, just from less than 1. So a negative sign, that's what that little negative shows. So 0.5, 0.9, 0.99, if you had to test it that way. Just to give you an indication of what's happening inside this asymptote. And you could do the same for the oblique asymptote, y equals x minus 3. Okay, so we're going to look at the final graph, which is here, and I'll quickly sketch it for you. And this is what it looks like. We would have done some testing and found that as we approach negative 1 and positive 1 from inside that range, it approaches infinity. And we found that this was the intersection point anyway. We also found an intersection point out here. Okay, so what we end up with is an asymptote that looks like this, passes through that point and continues. And we also end up then, there's a third region which is down here, and if I can squeeze it in, that would look something like that. Okay, an asymptote down the bottom. Okay, so there's a more complex example of how to sketch a curve with both an oblique and a vertical asymptotes. Probably the most difficult you'll see in the Extension 1 course, but particularly looking at the method of splitting the fraction to get the oblique asymptote, and then just testing as we approach the asymptotes. Okay, I hope you went right. If you didn't get this one right, as I asked you to try it, just make some notes to make sure you understand the different components of this process. Thank you.